Hello, we are Group 14 and the following presentation is for our senior design project, the Motor Assisted Cooler or MAC. Meet the members of the MAC team. We have two computer engineers which consist of myself, Min Park, and David Crumley, and two electrical engineers, Akil Ahmed and Fong Thi Duong. The description for this project is to design and create a motor-assisted cooler which will enable the user to transport cold beverages and/or food items to and from their vehicle with less strain on their body. The motivation for our project is to make sure our device can traverse all sorts of different terrains, such as sand, gravel, grass, and concrete, keep our cold storage items cold for longer, and have fun while doing it. To accomplish this task, we have set up our goals and objectives to four main parts: the motor-assisted cart for mobility, our Peltier cooling device to keep our cooler cold for longer, power distribution to manage our power consumption from the motors and cooling device, and finally our solar charging component to keep our cooler running for longer by increasing the battery life. Here we have our specifications for our device so far. For the batteries, we have our discharge and charging times. We are currently running two 12-volt batteries running in parallel, which provides us with 2 hours of continuous use. Our current design to charge the batteries with the use of our solar panel takes up to 6 hours. During testing of our Peltier device, it took 20 minutes to lower the temperature of a 12-quart cooler to 50 degrees. A thermostat with a relay to shut off our refrigeration system so it doesn't need to be constantly running, one solar panel that outputs 50 watts of power, and two motors that give out 155 each, or 310 together, ounces per inch of torque with a maximum of 480 RPMs. Here is the visual representation of the four major components alongside our task allocation. Akil and Fong are in charge of our power distribution and battery charging, while I was in charge of the refrigeration system, and David, who had the task of making our system mobile, who I will now pass it off to.
All right, thanks for the intro, Min. My name is David Crumley. My major is computer engineering, and I am responsible for making the motor-assisted cooler motor-assisted. So we'll get started with the next slide by showing the system block diagram and outlining the major components of the motor control system. Okay, so the motor control system consists of a slide potentiometer, which is used to read the user's input as it begins to pull or push on the handle of the cooler. This potentiometer outputs an analog voltage between 0 and 5 volts. So the ADC of the microcontroller will then convert this analog signal into a discrete value, which will be used to determine the desired speed of the motors. After that, a PID control algorithm will be implemented to ensure that the speed transitions are smooth. This will all happen within the microcontroller. The all effects encoders, which are located in the back of the motors, will be used by the microcontroller as a feedback loop to calculate the error used within the PID algorithm. So once the output of the PID controller is calculated, the duty cycle will need to be adjusted, right? So the output of the PWM of the microcontroller will be sent to the gate driver integrated circuit, which will boost the power in order to operate the MOSFETs. After that, that power will be sent straight to the motors, and the output speed will be the result. So the PID controller is really the heart of the motor controller design. We can see from this block diagram that the desired speed will be calculated from the ADC value, as stated earlier. The error will be calculated using the Hall effect sensors from the back of the motors. This all will be implemented in the MCU, and the coefficients that we use in this algorithm here will have to be determined through testing. So we'll set some certain values here, and we'll see how the output acts, how smooth it is, and how quick it reacts. And through those tests, we will adjust these coefficients accordingly. So once the output is smooth and is responsive enough, then we can set those coefficients in stone, and the PID algorithm and the controller will stay the way it is. But we have to make sure that these transitions are smooth and that they're fast enough so that the user doesn't feel the motors kicking in. We also have to make sure that we have no unwanted oscillations in our design. So the input measurements, the PID calculations, and the output PWM signal are all going to be taken care of using this PIC 18F14Q40 microcontroller. This microcontroller was chosen for its low cost and low power consumption. The average current draw shown in the table, as we can see, um, during the time that it's fully operational, at 6 milliamps, when everything is operating to the full capacity. The output PWM signals and making all calculations, right? So this is around a quarter of the current draw of a comparable ESP32, which you can see on Arduino, while it's in sleep mode. This is one of the main reasons why we chose this microcontroller, because it's low powered and also provides all the functionality needed for this subsystem. So the main advantages of choosing this microcontroller over a more powerful one are the price and the power consumption. It's only $1.08 per microcontroller, right? So based off these metrics, we decided this would be the best microcontroller for this motor control system. It does everything we need, and it's very low power consumption and low cost. So next, we're going to talk about the circuit that will be controlled by this MCU. So what we have here is the actual MOSFET circuit that will be powering our motors, and it'll be controlled by the MCU. And the circuit is known as a full H bridge. The four MOSFET transistors that we can see here are going to allow for the current to flow in both directions based on which MOSFETs turn on and off. This is going to give our project the ability to move in forward and reverse. So the major components of this circuit are the H-bridge gate driver, the MC33883, and the MOSFET transistors themselves. Every other component that we see here is for protection and current maintenance. For our H-bridge circuit, we have decided to go with the IRF Z44NPB. This component was chosen because of its low internal resistance of only 17.5 milliohms. This is a characteristic of the HEXPET power MOSFET category of which it belongs. This low resistance is important because it means that we can have 10 amps going through this transistor with there being only 1.75 millivolts across the transistor. This meaning more power to the motor. In order to turn our MOSFETs on and off at the right time and in the right way, we've decided to go with the MC3883 H-bridge driver. Because this IC is a full bridge driver, it takes 4 inputs and has 4 outputs, which go to each of the MOSFET transistors. The advantage of the full bridge driver over the half bridge is that it provides protection to the circuit by assuring that the wrong transistors aren't on at the same time. This can cause shoot-through and short-circuiting of the battery if not protected. This particular driver supports up to 100 kilohertz frequency, which is more than enough for this particular component. So the last component decision that was made for the motor control subsystem was the actual motors themselves. To power this cooler, the motor that was chosen was the Lynx Motion 12-volt motor shown here. This motor is the best 12-volt high torque motor that we can find, which also has an encoder and gearbox built into the case. Having this gearing means that the motor can provide more torque at a lower current draw and maybe a higher voltage motor without the gearbox. The motors will provide us with over 300 ounce-inches of torque at a max RPM of 480. While the RPMs are lower than without, and if it didn't have the gearbox, this is actually beneficial to our project because we're not looking for high speed, but high torque. Alright, so now that I've talked about each main component of the motor control system individually, let's look at the final schematic of the entire system. So there is included a safety feature which was not previously mentioned. This is the user presence switch, which will be implemented as a trigger on the handle of the cooler. This safety switch will ensure that the system will never run without a user in control. There will also be some external programming pins for the tuning of the PID gains, as mentioned earlier, also for the inevitable debugging that will occur. So now we can see the actual PCB layout of the circuit. As you can see, we gave plenty of room for the wider traces needed for the high current of the motor. Also, the MOSFETs will be sitting off to the side of the PCB to allow for good heat sinks to be mounted to them. Special care was made to remove all 90-degree turns in the traces, and also we wanted to make sure that there were no parallel lines on either side of the board, which can cause a capacitance to form between them. Also, a 5-volt switching regulator is implemented within the PCB to power the MCU and potentiometer. So before the complete circuit design and PCB layout was finalized, we wanted to make sure that the circuit actually worked. So we decided to test it on a breadboard. And we can see here in this picture the full circuit from before implemented on this breadboard. For the power supply, we used the power supply provided in the senior design lab with 2 channels, one at 12 volt and one at 5 volt. What we can't see in this picture is the potentiometer connected to the inputs of the MCU. And what we found is that the circuit worked. In the next couple slides, I'll show the output showing positive polarity and negative polarity on the oscilloscope. So let's go to that. So we can see here the output waveform with a 50% duty cycle. Now this result was when the potentiometer was at the first quarter of its full swing. We can see that we have a nice 50% duty cycle constant pulse width modulation output. We can also see that the output isn't exactly 12 volts. This is actually due to our gate driver being damaged during soldering. After some other testing, we realized that it wasn't providing enough voltage to completely turn on the high side MOSFETs. They were only getting about 3 volts, while the lower sides were getting the full 10 volts. We believe that with some new parts ordered, this won't be a problem. So on this slide, we can see the output due to the potentiometer being in the third quarter of its full swing. And we can see that our minimum is around negative 9 volts and our maximum is close to 0. And we're still having the same errors mentioned before with the output not being the full 12 volts. We're very confident in our conclusion that the gate driver is damaged because during our early testing, we were getting the full 12 volt swing. And so finally here we have the actual physical layout of the motor control system. So on the cart in which the cooler will be sitting, the handle will be actually replaced with a custom handle that we've made where the potentiometer sensor will be attached to that handle to measure the user input. The handle will be 2 pieces that will actually telescope in and out, and the potentiometer will read the telescoping of the handle to convert that to the desired speed. The motors here will be attached underneath, and their drive will be transferred using a belt. The safety handle, as we see, will be mounted right there on the handle. Easy access for the user. So that concludes the motor control system. Now I'd like to pass it back to Min so he can talk about the refrigeration system.
All right, thank you, David. And now on to the refrigeration. The refrigeration method we chose for our project was by using a thermoelectric Peltier device. This particular method of cooling doesn't require any moving parts such as your normal house refrigerator or air conditioning unit, which uses liquids to move back and forth through the system. The Peltier instead uses an electric current to cool a targeted area. As you can see from the middle image, this device consists of an equal amount of N-type semiconductors and P-type semiconductors, which are placed in series with each other throughout the device, which is then covered by 2 ceramic tiles. On one side of the tile, it absorbs the heat, and with the absence of heat, we are left with the cold, which is where we get our cooling side. The other side rejects heat, which is coming from the cold side, making it very hot. While testing this device, it brought up 2 problems that we encountered. The hot side of the Peltier device was getting too hot, which could cause the device from burning out, while the cold side of the device wasn't transferring any of the cold into our cooler. To solve the hot side problem, we added a big heat sink and attached the fan to disperse the heat evenly in a safer fashion, and used the same solution for the cold side of the Peltier, using a smaller fan to create an airflow into our cooler. The image to the left is the final refrigeration device that we will be using for our system. All 3 items require 12 volts from our batteries. The Peltier device can take up to 10 amps of current, but during testing it only drew 4.5 amperes. The smaller fan, which is attached to another heat sink, draws 0.9 amps, while the bigger fan takes up to 0.2 amps, which is attached to the hot side with the bigger heatsink. During testing, our Peltier refrigeration device was able to get down to 40 degrees Fahrenheit in an hour with no items within the cooler. But when we added a plastic cup with ice in it, it took half that time. Because our design was using a cooler for its exterior, we concluded that our device didn't have to be on the entire time of our cooler was in use, thus draining our battery. To that end, we used a small thermostat with a relay with an attached sensor to measure the internal temperature of our cooler. This device draws 65 milliamperes of current and requires 12 volts from our source. We set the relay to shut off once the temperature reached 40 degrees inside the cooler every time without fail. We then set the temperature ceiling to 42 degrees to turn our refrigeration unit back on until it reached that 40-degree mark. These are the final items used during our testing of our cooling system, which consists of the Peltier refrigeration device, a 12-quart cooler made from styrofoam, and a temperature control unit to which the former and latter is ready to be used in our final design.
Thank you, Min. Now I will go to the power storage part of the project. The expected design will be based on maximum power point tracking. The reason we wanted to charge our battery through MPPT, we just did not want to waste our power when it's available and try to keep our battery charged all the time. So it should be able to provide current to its load, and people can stay for longer period of time outside, or this device should be able to provide power for a longer period of time. The solar panel that we chose is 50 watt, and it is capable of giving us an output current around 2.8 during the daytime, and the output voltage will be around 17. And through maximum power point tracking charge controller, we will be able to deliver all the power to the battery so it can charge in a less amount of time. We are using two 9 ampere hour 12 volt lead acid batteries to drive our load. The following figure is showing the charging stages of the battery. We will be building an algorithm in microcontroller, and this algorithm will shows the charging stage of a battery on our LCD display. There are different parts in our solar charging circuit, and we started to test them one by one. The first thing we implemented is a buck converter and tested it through function generator and oscilloscope, and it can be seen that we were able to get a pure DC on oscilloscope by changing the duty cycle of input signal. We used a 50 microhenry and 470 microfarad capacitor and some diode to build this circuit. The second circuit that we tested is switching circuit. We wanted to have a switching circuit that should be able to turn on and off buck converter with higher frequency. So this circuit is capable of taking care of frequency from 20 to up to 50. We tested it with 20K, and the result will be shown in next slide. As I said in my previous slide, we tested this circuit for up to 20 kilohertz. Since 20 kilohertz is good enough for our design, and it can be seen by giving a 20 kilohertz signal on our function generator is turning on and off our switching circuit, and we can also see the 20K output voltage on an oscilloscope. The next step in our design was to charge batteries using buck converter, switching circuit, and drive this switching circuit through microcontroller. We just did it, and by varying the duty cycle in microcontroller, the output voltage of the buck converter was changing, and we just charged our battery by giving a DC voltage at the input of the buck converter and changing it at output of the buck converter. And the result can be seen in a figure, and we have a DC showing on the oscilloscope, and this DC voltage is used to charge the battery. When we tested our circuit with function generator, we were able to get a pure DC at the output of the buck converter, but using a microcontroller giving us some ripples at the output of the DC voltage. So we are considering different options, and one of the options is use Node MCU instead of PIC because it has fast time response. We are also working on LCD display, reading sensor data. After doing these two steps, we will be actually implementing our algorithm in microcontroller and move to the PCB. The following figure is the simulated circuit of solar charger. In hardware, we made some changes for different parts, like we used different values of capacitor and inductors. We used totally different switching circuits since the simulated switching circuit was not working on a hardware. We still need to test our LCD and current and voltage sensor. After that, our circuit will be pretty much done. The only thing which will be left is algorithm, and we already worked on algorithm. Since the main parts of a charging circuit are already tested, the only thing which is left is LCD display and reading sensors data. We already assigned those pins to LCD and sensors and made our PCB ready for order.
So the voltage regulator that we'll be using in our project will be a step-down switching regulator LM2576 adjustable version. This regulator offers a wide range of input voltage up to 40 volts and is able to try a 3 amp load with excellent light and load regulation. This regulator was designed to minimize the number of external components to simplify the power supply design. Since it is a switch-mode power supply, its efficiency is significantly higher in comparison with popular three-terminal linear regulator, especially with higher input voltage. This regulator has an external shutdown as well as the thermal shutdown for full protection under fault conditions. In our project, we will need one to step down the 12 volts from the battery to 5 volts for the motor controlling board and the sensor. We need another one to also step down the 12 volts to 5 volts for the microcontroller and the LCD display of the charger. Below is the schematic of our voltage regulator. The input voltage will be 12 volts and the output will be 5 volts. We also include the formula to calculate the resistor values for R2 and R1. We choose R2 will be 3 kilo ohms and R1 will be 1 kilo ohms to produce the output voltage of 5 volts. We perform the circuit testing in the senior design lab. We use the through-hole components because it's easier to plug them into the breadboard. We inputted 12 volts from the DC power supply to the circuit and successfully received 4.99 volts, which is 5 volts from the multimeter. So moving on to the administrative content. This is the current progress of our group. We have most of the required research done. We also completed the designing for hardware and have all of the necessary components. We have ordered the PCB and waiting for it to come in around 2 weeks. In the meantime, We will be testing the coding for the ADC and try to display the battery percentage on the LCD. Our implementation and overall progress are on track to be completed on time. The table below shows the outline of the expense for the project. These are just the current line items that we have so far, but we seem to be on budget. More components that we listed were bought, and many of these were used for prototyping purposes. We pay everything by ourselves. Our functions work together as we try to help each other out. Thank you for your listening. We are now open to taking any questions.